So as I said, I'll start with the first question, but then we're hoping to get more questions from the audience. And so the question I wanted to start with is especially after signing stock. Do you think the transformers have actually any inherent advantages over CNNs, or is it actually all just because of improved training practices, more data augmentations, better optimization? Yeah, what do panelists think about it?
Yeah, I'll start because I have the mic and then I'll pass it along. It's a hard question. I think they kind of do a little bit, but maybe not what people expect. So I think the transformers have real advantage when you start scaling up. Before we scaled up transformers, we actually scaled up ResNets a lot. And we were hitting very diminishing returns, and they were getting extremely costly in terms of compute and memory usage. And we found that with WITS, basically we kind of can push the problems of scaling up a bit further. And it's cheaper to have large scale WIT for training than large scale convnets. And I have not yet seen evidence of the contrary. I'm also a fan of ResNets, and I also regularly try to push them again to large scale pre-training, but so far it's easier with transformers, let's say. I partially agree with signing that it's not clear that attention is like the key thing that makes all the difference. It initially looks like it because it looks so very different from convolution. But yeah, I'm not 100% sure on that.
Yeah, I think from like a multimodal perspective, if we want to find a single model that works across different inputs, then the fewer assumptions we make, obviously the better. And I think some of the assumptions that we make with CNNs, like translation invariance being a good thing, that's not what we want for spectrograms and audio, because you have frequency and time, you have different access now when you have 1D waveforms. So I like removing the assumptions baked into the model and the invariances, but I agree that a lot of this is sometimes training tricks. And I think that it's very difficult to compare because we have so many papers coming out and everybody's obviously training with slightly different setups and hyperparameters. And, we need something that's more uniform to kind of compare, but that's what I feel.
Just to get signing in a loop, and maybe that's a good time for him to join also in his opinion. So the question was, do you think transformers have any inherent advantages over CNNs, or is the performance boost just mainly due to improved training practices?
Yes, I completely agree with the previous comments, like the less inductive biases and the scaling behavior. These are, I think, very strong properties of transformers. I wanted to come back to attention part. So typically we have, in the vision domain at least, we have images and 16 by 16 patches. And I think, as we scale these models up, I think eventually we will, part of it, we already start to seeing it. Eventually, we will see these transformers being used in videos in a long form format. Like I'm talking about in tens of seconds to minutes of the data. And in that context, I think this long global attention mechanisms can really shine in extracting what's there in this long sequence of input in high dimensional space. So yeah, I'm hopeful for the attention part being the game changer as we scale these models up.
Okay, so the only thing I have to add is the permutation invariant structure of it is really useful for 3D data like point clouds. And I think it's very natural to use transformers there. And in general, the other thing that has been really useful is like the variable lengths. Like you can actually send in variable length at inference time, which is another really, really useful property. So I think both of these properties are actually extremely useful. You can combine them in hybrid architecture. But I think like fundamentally, it is something that self-attention lets you do, which you can't do with other models.
The only thing that I would add to what's already been said, I agree with Arsha about the point about the multimodality, that it seems to seamlessly tie multiple modalities together. I also like the fact that the self-attention is inherently we can sort of exploit it to remove redundancies, which are there spatially as well as temporally in videos. I think to me that seems really interesting, that you can sort of manipulate the self-attention layer and try to extract that out of it.
So before Sunny, before you go, I also wanted to, so lots of claims have been made about, transformers are better suited for big data regimes and that they scale better. And actually in your ComNext paper, you also studied that and didn't find a lot of evidence that this is necessarily true. So maybe in addition to what you were gonna say, maybe you can comment on that as well.
Yeah, sure. So I think, yeah, this is a kind of assumption, and I think ComNext is a paper to really challenge this assumption. And in the future, I think we need to continue doing this. And to me, I think, as I said, like ComNext is a scalable architecture, but I just want to add to it. Like I still really like transformers, and I think one thing I particularly enjoy transformer is we can actually learn a lot of things from other domains. A lot of new advancement is not from vision, it's from NLP. This includes like kind of like architectural innovations, but also kind of like hardware and kind of infra level improvement. And this is something I think that can really bring different communities to get together.
Okay, thank you. So we have a virtual question. So I guess following NLP, when are we gonna see 100 billion parameter VIT model? Maybe this is a good question for Lucas.
Yeah, I don't like this question. I think you cannot compare the number of parameters across domains. Like, for example, in NLP, you have the whole dictionary, lookup table, and word or token embeddings and so on that blow up the parameter count. So I'd rather not compare parameter count between vision and NLP models, but I would rather compare the total compute spent, like during training or maybe inference per example or something like that. I think personally these are more comparable and better ways, it's not perfect, but better ways to compare their capacities. And if we look at that actually in our scaling vision transformer paper, where we tried to do exactly that, push like transformers in vision to the largest scale that we can do currently. We can compare this like total training flops and the training time to NLP ones. And I think we were maybe a quarter of the largest NLP models at the time we published this, which was already a year ago. So now we're further behind again. But yeah, we're getting there slowly but surely. But not in terms of raw parameter count.
Any other thoughts on this? Okay, so let's go ahead with a question from the audience.
Okay, so I have several questions, but I will ask only one and give others a chance, and then I will go back in the queue. So I don't have any preference for ResNet or any CNNs or transformers. So, but I do have preference that we should model the world as it appears. So it has statistical correlations. So let's be honest about it. So we should model statistical correlation. But at the same time, I don't want to make any assumptions like some of the models may do. So the question really is that, do you think GMML, and if you miss the morning talk, you can call it MAE or you can call it SIMIM, do you think that that's a very nice way to model the inductive bias and global information dictated by the data? And in my argument, I would support that we can use GMML and outperform CNNs on only 1 to 2,000 images as well.
Okay, I'll say something. Maybe Sean, you can follow up on that. So I think if you look at like self-supervised learning, we have a lot of different kind of like pre-training objectives or pretext tasks. Like originally we'll have like colorization, jigsaw puzzle, and so on, right? And then we'll have a step change, like contrastive learning becomes like kind of a dominant paradigm. And then we'll have this mass image modeling. And to me, I think they are all reasonable ways to model like so like the intrinsic like information in your data. it's still kind of unclear to me why kind of MAE is better than contrastive learning, and maybe like you trying to do some work in combining two things together, or I fear there's a couple of papers doing this. So I think in the future, I won't really assume that MAE is the only way that we can actually model the real data, because there could be like, fancy ways, especially considering now we have like really good generative models, right? Diffusion models and so on. Yeah, I think in the future we should, again, like keep an open-minded and then explore more diverse pre-training objectives.
Yeah, so for me, I consider like the masked modeling stuff is basically a very nice way to add data augmentation. And so one of my complaints with contrastive methods has always been that we have been designing data augmentations for that particular domain. We've done like multi-crop and like all of these augmentations, which have been very much exploiting the nature of the data sets that we're actually training on. And with masked modeling, it's more general, where we are actually now, and you can sort of argue that patch modeling is also sort of exploiting the inductive bias in the data by basically saying that these patches, like 16 by 16 patch actually has some like local correlations and so on. But I do think like we're moving, this is a step change from what we did with earlier data augmentations, where we were like really handcrafting all the values. So I think in that sense, we're making a large progress. And I do agree with you that we are like modeling local correlations. Again, like Signing said, I'm not sure if that's the complete answer. There are certain places where masked modeling, it's to me not clear whether it'll actually work, for example, in extremely low data regimes like low data fine tuning or like low data sort of downstream performance or like low label. And so I think in the future, probably like there needs to be some kind of predictive modeling. Does it have to be pixels? Does it have to be like just like local masks? That's not clear.
What do you quantify as low data? We are getting best results on 2000 images.
Pardon me?
We outperform CNNs using group mass model learning, even on 2000 images.
No, so what I mean is basically when you're fine tuning, let's say like one label per image, or you're fine tuning with like 5 labels per image. So in general, for all of these things, and it doesn't matter, like it basically what ends up mattering is not really the transformer architecture, it's the sort of pre-training objective that you're using. Are you predicting pixels when you're doing all of this stuff? And the representation that you end up getting by doing that is really good at full fine tuning when you have lots of data, but when you have limited amount of labels for fine tuning, it doesn't seem to be performing as well.
Do longer pre-training and then use MCSSL.
I mean, people have tried that, doesn't seem to work. So
that's very interesting. I would like to take this discussion offline then,
yeah,
and have it because we have a very different perspective, and I think I don't agree with you.
Okay. Good to know.
Okay, we have another virtual question. Clearly, there's a growing gap between industry and academia. So lots of these transformer-based models are getting bigger. We're training them on more data. We're training them for a longer time. So requires lots of resources. And yeah, so where do you see this going? Is there like, what's a path forward for, I guess, like, academic researchers and students in this domain? What do you think?
So yeah, the scaling is fairly important, as we all know, in transformers. So, and I don't see a clear answer on where academia can really kick in the scaling perspective. But I do think that there are many other important questions that must be answered, and these may not require large scale compute. Robustness is maybe one example. Robustness to the corruption, noise in the data itself, or when we design this self-supervised learning objectives or MAE, there are data specific still noise that we can think of, like contrastive learning, as Ishan was mentioning. Sampling views oftentimes requires lots of prior knowledge, and even so, it creates noise. Then how can we design these learning objectives that can be robust to these noise issues? I think these questions can still be answered without large scale compute.
So I'm also interested in Signing's perspective, since you're going to be studying as a professor soon.
The honest answer is I don't know. I'll see if I can survive. But to be honest, I think I have like maybe two things to say. One is like we really want to explore more diverse ideas in this space. So if you want to kind of like explore diverse ideas, maybe your bottleneck is not like the number of GPUs, but like number of people who can actually explore different things. And the young brilliant minds, like the fresh graduate students, they can be really good at this. Second thing is like I think for computer vision, we need to really identify the breaking point in the scaling law. Like we don't really have a scaling law in computer vision in self-supervised learning yet. But if we can identify that, I think like even with academic resources, like maybe 4 GPUs or 8 GPUs, we can already train a model that you are confident like, oh, actually, if I can extrapolate this kind of like scaling behavior and train bigger models, our conclusion can still hold. So this is something I feel like we should strive to look for.
Mhm. Any other thoughts?
So I think the other problems to look at are actually problems in 3D, which have been like traditionally ignored because folks have really focused on image recognition, video recognition, which are compute intensive. And like for the 3D work that we did, for example, back in the day at FAIR, we were using a single GPU to train a model. So I mean, that's possible. Like I did that just as a challenge because I wanted to cap the number of GPUs I was using. And it works. I mean, you are actually able to train and solve interesting problems at that scale as well. So I think 3D data is something to definitely look into.
Yeah, I just wanted to add to that there are also a lot of really interesting problems that don't need huge compute, or that we can start from something like pre-extracted features. For example, modeling stories, things like movies. For that, we're anyway going to start with pre-extracted features because we want to cover things like 2 hours of video. And also like adding on to the point about 3D, there's lots of problems in sound and speech and multimodal fusion that haven't been solved yet. And we're still at like very basic things like how do we represent the inputs? And I don't think we need huge amounts of compute to solve those.
Yeah, maybe I want to give a little bit of perspective like about VIT and that it needs large compute and large data and so on. Initially, that was kind of by design because we had a previous work with CNNs where we noticed like, oh, when we scale things up, everything works a lot better. And then we want to look, okay, can we find something even more expressive than CNNs and where we throw away the inductive biases because we want to learn them all from data. And then that was with VIT. So it's kind of by design, and we're surprised that a lot of people then actually spend a lot of time trying to make VIT work and succeeded a lot to make it work on less data. So I think that's pretty cool, actually. And another thing that I see is recently starting to become quite interesting, or I see lots of fun papers about, is taking some pre-trained models like be it VIT or ResNets or from models from CLIP and so on, and plugging them together in some ways. And then just try to learn the different mappings between them and use those to solve cool tasks. I think there is probably a lot of creativity that can still be applied and doesn't need massive compute, massive data and so on, because it starts from the model that already knows a lot. So yeah, that's what I would like to see a lot of.
And I'd just like to add that, there's also other problems related to explainability, and also trying to make model sizes smaller so that they can actually be applicable in the real world. Both of these problems do not necessarily require large scaling, and there's a lot of work to be done there to get these things in production. That is all very useful research.
Yeah, thank you. Another question from the audience.
Yeah, we've seen quite a few attempts to modify the underlying attention mechanism to break the quadratic bottleneck, things like reformer, linformer, et cetera. But it seems like those tricks don't always really generalize outside the original data set or the original task. And when we look at like what's been applied now in vision, we're seeing things like swing transformer or perceiver that just straight up bypass having, a large n by n that scales with your number of actual tokens in the first place. So do you think there's still a benefit to trying to like find ways to optimize or to like speed up the underlying attention mechanism? Or do you think that things like perceiver and swing transformer sort of allow sort of break that as being an actual bottleneck and mean that there's maybe greener pastures to be pursued?
So I can say two things. One, yes, some of these specialized techniques, when we scale things up, we don't really see huge benefit. Yes, but I still would like to encourage us to think about better ways to model these architectures, because some of those are, can be effective. And we see some of these examples in the community as well. Like there are lots of techniques that we really need to use in training large scale models. And second, maybe connecting to the previous topic, I'm all in for bringing priors to transformers, especially in the small data regime. When we don't have enough data to learn from, when we don't have enough data to generalize, then these prior informations are crucial. And we know this from the history of computer vision, I guess. So yeah, that's my 2 bits of thoughts.
I think overall, the other sort of thing to keep in mind is when you're optimizing any of these architectures, when you're saying quadratic complexity, all of that is theoretical. And so it needs to be tied into a particular hardware for it to actually be useful. So that's another thing to maybe look at, as like Shalini was saying in the previous answer as well. So looking at approximations, there might be even like the current quadratic complexity, just the vanilla self-attention, does it actually fit into hardware for a particular deployment scenario? I think that's the other thing to like look at. Maybe it's not as interesting, but like there are 2 ways of solving a problem, right? Either you approximate the exact solution, or you basically try to like change the behavior of the exact solution to more like to suit your like inference time constraints. So that's the other approach of doing it. And so far, I think the first one hasn't, like, you keep seeing it breaking because we haven't understood like what the limits of the original exact formulation are, right? Like all of us are really trying to understand how self-attention is useful, or is cross-attention the thing? Are there like modifications to it? So maybe it's a little bit early to start optimizing all of that until we understand how it's applicable and where it starts breaking. And so maybe that's why we haven't seen it work as well.
I also think that going through what you say, you need to match the hardware too. And I think people are especially pessimistic because they see this quadratic or behavior. But in the original white paper in the appendix, we actually timed this up to resolution, I think 512 by 512, and it did not really fall off speed-wise compared to just ResNet at that resolution. Like at 512, maybe it started to get slower than, noticeably slower than ResNet, but before that, not at all. So this is a kind of the big O notation thing, where for most ranges that we actually use, the big O doesn't really kick in yet due to the hardware, basically.
Just one final comment to make. I think it really depends on the task. If you look at computer vision task, we don't need like, super long range context modeling yet. Like for example, like as Lucas said, like if you just extend to like 512 by 512 image, is this like really super long sequence? Not really, right? So I would imagine like actually vision transformer can totally handle it in terms of like accuracy and like runtime, it will be good. But will we have like really kind of long range context modeling tasks in the future? Maybe like, for example, in video tasks, like, if you want to really have a reasoning task, like from very long, like maybe hours of a movie, can you achieve this task? Like maybe we should just invest more into developing more benchmarks and more tasks in vision.
Thank you.
Okay, Jiting.
Oh, hi, thanks. So I actually have a question. I'm very curious. So I'm very surprised that, so before the deep learning era, actually the visual community, the visual recognition community were dominated by like the concept of grouping and these segmentation and these relations. I wonder, actually, in terms of the specific form of self-attention, is it kind of having an advantage of CNN in terms of like being closer to this kind of pre-deep learning era works and also kind of better modeling the mid-level representation better similar to human vision? Because I can't help thinking about it, given the pairwise similarity modeling, which makes it very similar to like spectral clustering method and those early methods in visual grouping. So and are these the kind of sources that's maybe some of the interesting emerging behaviors in like transformers, like emerging segmentations, the additional robustness out of distribution generalization? So yeah, really want to hear some more thoughts.
I can quickly share one thought on that, Juding. So I think you're right in that the sort of CNN's sort of formulation is somewhat inspired by the human visual system. That said, so that's compelling to sort of introduce those priors. That said, I don't necessarily think that we know that the human visual system is a very good learner. That said, it's also been shown in many tasks that the AI systems can actually outperform humans. So that is not necessarily the state of the art or speed of light in terms of learning. So if there are other architectures, machine learning architectures that can perform better, I think it's worth exploring those. That's my 2 cents on that.
So I can talk about the emergent behaviors a little bit. So I think one of the reasons this has been very useful in the transformer architecture is the fact that we've gotten rid of pooling, which was essentially like context insensitive, where you would just average things out in this group because, well, we couldn't handle, say, high resolutions and so on. So I think that has been actually pretty good. One, getting rid of pooling, or second, actually having like cross-attention based learned pooling. I think both of these have been really good, because now when you're actually talking about grouping together things that are related, you can actually do that. You have a learnable mechanism to do it. Whereas in the past, we've kind of always, like the grouping stuff has always basically been a fixed kernel, which we designed for that particular data set, which is completely instance agnostic and just ends up pooling stuff there. So that's been pretty useful. I think that has actually been a very nice property.
Okay, so we'll have one last question and then we'll wrap up. Please go ahead.
Thanks a lot. I would like to thank you first and all the other organizers for great efforts for the workshop. A quick comment on the small compute. So if as a community we stop blocking the work because it is not trained on ImageNet, that will be really helpful. It took us around a year to do 400 epoch on ImageNet. So, and it is always very painful to see a great research idea not being published because of the compute resource, but later on the similar idea or same ideas are picked up and then become world-best methods. So coming back to the architectures and moving forward, would it be more beneficial if we constrained the attention and then focus on how to share information between those constrained attention? So maybe some kind of messengers between the controlled attention and then communicating. Maybe that will solve a lot of problems. That will solve bias problem, that will give us the flexibility to model the global context. And more importantly, that will allow us in 1 second, 10 seconds, maybe a few minutes worth of video.
I can ask a clarifying question for this one. Is cross attention something in the lines of what you're thinking? Because that also can be viewed as a form.
So not completely cross attention. You see the attention mechanism is very beautiful. If you study the attention mechanism itself, and as you go deeper, one token can represent everything. So you don't need many tokens. So define messenger tokens and then share everything between them. You should be able to scale without any problem. You should be able to model the local context as well. Any thoughts on that?
I can try. So do you mean have a few like global tokens and then have that kind of communicate with the rest? So that in the sense of like the big bird architectures that had global tokens and then local ones, or even is that kind of what?
I guess I need to draw. So this can be in several different ways. There is no specific way. All you need to do is you need to control your attention mechanism in such a way that you do some local attention mechanism first, and then you do global attention mechanism later on.
Yeah,
And
so-
then if you go for 5-6 blocks, then any token will represent anything, because everything is attending to everything. Just take anything, any token, and start interaction between them in the deeper block. It should work. You have compute, you can do it. We cannot.
Yeah, I think you mean something like the hierarchical attentions, right? First smaller blocks.
No started convolution, no downsampling, no pooling operation.
Yeah,
All
but
pure
all
transformers.
attention, but all with attention, right? Like first small local attention, maybe everywhere, and then another attention things that looks at the results summarized by
Yeah.
these local ones, and then higher and higher level, right?
Because if you study the attention mechanisms as you go deeper, every token is attending to everything. At the end, there will be 3-4 representative token. If you look at the fairly, if you look at attention, study it, if there is some plain region that will start to get more concrete attention, that will start to have higher response value, just because that will start to encode the information from every other token. So because as we are doing multi-head self-attention block after block, after 5-6 layers, every token has information about every other token.
Yeah, but it's not enough to have just all the information collected. You also need to process it.
So what
and
I'm
then
saying
after you
that
process it,
once you are
comparison.
into that stage, after that, define global tokens from each representative area and have interaction between them.
Yeah, there are some papers like this. I think one is, for example, called Token Learner, which does pretty much that, like a bunch of attention blocks, the regular ones, and then it has a few summarizing tokens that, look at these the outputs of these several layers of regular attention, and then continue only with these, I don't know, 5 or 10 summarizing tokens. But again, a few layers of processing them and then output.
And how about adopting them in such a way that you can learn how to attend and where to attend and not restricted to the square grid.
This I don't understand, because attention is learning where to attend.
It's essentially at the end of the day graph. You can learn the nodes of the graph.
So I think, so we presented a work earlier. We have a talk on this, I think on 4A. We have a paper called Group VIT, where we essentially did very similar. It was inspired by the Token Learner. And you're right. I think the Token Learner and Group VIT, both of us, we kind of, showed that you can sort of summarize the information of the tokens, all the spatial tokens into smaller groups, which is kind of what you're alluding to.
Yeah.
And in Group VIT, we essentially appended 4 learnable or, some n number of learnable tokens in the early layers. And then we collapse all those spatial tokens into belonging to one of those group tokens. And then we collapse the group tokens further at a higher hierarchy into smaller number of group tokens. So I think this idea, I think you're thinking along the same lines, is certainly possible and leads to computational efficiency. And I think there's quite.
We were doing it as well. I think in parallel to what maybe we predates your work as well. But what I'm saying is that then there is further flexibility which needs to be done, because then you are defining fixed grid attention. Are there any investigation into how you, at the end of the day, it's a graph. You can learn the graph structure itself. So is there any work going on? Maybe you don't want to share, maybe you want to present it in a paper or something. How's that graph? You can define, constrain it in a square grid, or you can let it go free and learn the attention where it should attend to itself.
But then it's input dependent, and for different input images, it attends to different parts. So
Yeah,
it's not
it's-
like you can fix the graph once and then reuse that for
Yeah,
other
of
input.
course, it should be input dependent, yeah. Otherwise, it does not make sense.
Yes, and then we
But is
add
there any
attention,
work which you guys are doing along that direction?
and then we are back to the attention mechanism, or
Yeah.
I don't see what you mean.
Yeah, essentially. Okay, thanks a lot.
Okay, so let's wrap it up. Let's thank the panelists.